March 15th, 1944. Anzio Beach Head, Italy. The captured Sherman tank sat motionless in the German maintenance depot, its olive drab paint chipped and scarred from weeks of combat. Oberf Klaus Hoffman approached the American medium tank with the practiced eye of a veteran mechanic who had spent 3 years keeping German panzers operational under increasingly desperate conditions. His toolkit contained the same wrenches and diagnostic equipment he used on Panzer IVs and the temperamental Panthers that had been arriving from the factories with alarming frequency. What he discovered under the Sherman's engine deck that morning would shatter every assumption he carried about American industrial capability and automotive engineering. The Ford GAA V8 engine hummed with mechanical precision that German tank engines had never achieved. After 800 kilometers of combat operations in Italian hands, followed by 200 kilometers of German use, the power plant showed wear patterns that suggested it could operate for thousands more kilometers without major intervention. The oil was clean, the cooling system functioned flawlessly, and the electrical components operated with reliability that exceeded anything in the Wehrmacht inventory. Hoffman had maintained Maybach engines that required complete rebuilds after 150 kilometers. He had cursed the fuel pumps in Panthers that caught fire spontaneously. He had watched Tiger battalions lose more vehicles to mechanical breakdowns than enemy action. Yet here stood an enemy tank that seemed designed by engineers who understood something German industry had forgotten during its rush toward technological complexity. The transformation began in Detroit assembly plants, where Henry Ford's production philosophy met the United States Army's desperate need for reliable armored vehicles. While German engineers pursued perfectionist designs that required hand-fitting and artisanal assembly techniques, American manufacturers applied mass production principles that prioritized consistency over craftsmanship. The MF4 Sherman represented industrial democracy in steel and mechanical components, a tank designed not for individual excellence but for collective reliability across thousands of identical vehicles rolling off assembly lines at unprecedented rates. The engineering specifications told a story of deliberate simplification that German designers had rejected in favor of increasingly complex solutions. The Sherman's suspension system used simple vertical vollet springs that could be manufactured quickly, installed easily, and maintained by mechanics with basic training. German torsion bar suspension required precision machining and careful adjustment that made field repairs nearly impossible. The American approach sacrificed theoretical superiority for practical reliability, ensuring that tanks disabled by minor damage could return to service within hours rather than weeks. Power transmission through the Sherman's drivetrain revealed American automotive excellence that German industry couldn't replicate despite superior theoretical knowledge. The Ford GAA engine produced 500 horsepower through proven automotive technology that had been refined in civilian applications for decades. German Maybach engines generated impressive power figures on paper, but suffered from fuel system problems, cooling inadequacies, and electrical failures that left powerful tanks stranded far from combat zones. The contrast became stark when captured vehicles entered German service unchanged, performing better than indigenous designs despite being manufactured by supposedly inferior American workers. The mechanical reliability that Hoffman witnessed extended beyond individual components to encompass entire automotive systems designed for sustained operation under combat conditions. Sherman transmissions, final drives, and steering mechanisms functioned for thousands of miles without major overhauls. German tank crews measured their vehicles' operational lifespan in hundreds of kilometers before critical failures required factory-level repairs. The mathematics of mechanical endurance favored designs that prioritized proven technology over cutting-edge innovation that hadn't been thoroughly tested under field conditions. By spring 1944, German tank recovery units were encountering abandoned American armor that told disturbing stories about enemy industrial capability. Shermans disabled by combat damage often showed minimal mechanical wear, despite extensive battlefield service. Engine components displayed manufacturing quality that German factories achieved only through expensive hand-fitting procedures that slowed production to unacceptable rates. The standardization of parts meant that field mechanics could repair complex systems, using components cannibalized from other vehicles, creating maintenance efficiency that German diversity of designs made impossible. The contrast extended to crew comfort and automotive refinement that German tankers had never experienced in their own vehicles. Sherman interiors provided spacious crew compartments with effective ventilation systems that kept fighting efficiency high during extended operations. German tank crews fought in cramped conditions where mechanical heat, exhaust fumes, and poor visibility reduced combat effectiveness after hours of operation. The American approach treated crew comfort as essential to mechanical reliability, understanding that tired crews made maintenance errors that caused mechanical failures. German intelligence reports from captured Sherman examinations revealed technical specifications that challenged fundamental assumptions about industrial priorities and mechanical design philosophy. The American tanks demonstrated that sophisticated engineering could be mass-produced without sacrificing quality, that complex mechanical systems could be simplified without losing effectiveness, and that reliability could be achieved through systematic design approaches rather than expensive individual craftsmanship. These discoveries contradicted Nazi propaganda about American industrial weakness, while revealing the true source of Allied battlefield endurance. The fuel efficiency of captured Shermans astounded German logisticians who had watched their own armor consume precious petroleum at unsustainable rates. Sherman engines delivered more miles per gallon while carrying heavier loads across more difficult terrain than German designs that theoretically should have performed better. The Ford V8 power plant burned lower-octane fuel that was easier to obtain and refine, while German engines required high-quality gasoline that was increasingly unavailable as Allied bombing destroyed synthetic fuel production facilities across the Reich. Maintenance schedules for Sherman tanks revealed American understanding of mechanical reality that German perfectionist approaches had overlooked. Scheduled service intervals reflected actual component wear rates rather than theoretical optimal performance, ensuring that preventive maintenance prevented catastrophic failures. German maintenance doctrine assumed that superior engineering would eliminate routine service requirements, leading to neglect that caused expensive breakdowns when components reached their actual operational limits. The American approach acknowledged that all mechanical systems required regular attention, while designing that attention to be simple and quick. The electrical systems in captured Shermans demonstrated automotive engineering sophistication that German industry had never achieved in armored vehicles. Wiring harnesses used automotive-grade components that resisted vibration, moisture, and combat damage. German tanks suffered electrical failures that disabled entire fighting systems because military specifications had prioritized theoretical performance over practical durability. American electrical engineers applied lessons learned from millions of civilian automobiles to create military systems that functioned reliably under conditions that destroyed German equivalents. Component interchangeability between different Sherman variants revealed American manufacturing coordination that German industry couldn't replicate, despite having centralized control over production. Parts manufactured in different factories by different companies fit together perfectly, allowing field mechanics to repair vehicles using components from various sources. German tank production involved multiple manufacturers whose components required individual fitting and adjustment, making field repairs dependent on specific factory support that was often unavailable in combat zones. The spring-loaded road wheels on Sherman suspensions absorbed battlefield impacts while maintaining contact with driving surfaces, providing mobility that German rigid systems couldn't match. Vertical vollet spring bogies could be repaired or replaced quickly using standard tools and common mechanical skills. German torsion bar suspensions required specialized equipment and factory-trained technicians for major repairs, making damaged vehicles total losses rather than repairable assets. The American design philosophy treated suspension components as consumable items that crews could replace rather than precision instruments requiring expert attention. Engine accessibility in Sherman designs allowed mechanics to perform major repairs without removing power plants from vehicle chassis, reducing maintenance time from days to hours. German engine compartments required complex disassembly procedures that made field repairs impractical for anything beyond minor adjustments. The American approach reflected understanding that combat conditions demanded simple solutions to complex problems, while German engineering assumed that superior design would eliminate the need for extensive maintenance under battlefield conditions. As German mechanics like Hoffman examined more captured American armor throughout 1944, the pattern became undeniable. Sherman tanks represented automotive engineering philosophy that prioritized reliability over theoretical performance, mass production capability over individual excellence, and practical maintenance over perfectionist design. These priorities had created fighting vehicles that outperformed German counterparts, not through superior individual capabilities, but through collective reliability that kept American armored units operational when German panzer divisions sat immobilized by mechanical failures. The revelation spread through German armored units like wildfire during the summer fighting of 1944. Tank commanders who had operated captured Shermans began requesting transfers to units equipped with American vehicles rather than the latest German designs rolling off production lines. Hauptmann Werner Schultz of the 21st Panzer Division wrote in his personal diary after commanding a captured Sherman for 6 weeks during the Normandy campaign, "This American machine operates like a Swiss timepiece, while our Panthers break down like carnival rides." The psychological impact on German tank crews was profound and demoralizing. At the Panzer Lehr Division's maintenance workshops near Caen, Chief Mechanic Feldwebel Otto Brenner documented failure rates that told a devastating story about German automotive engineering. Of 45 Panthers that had begun Operation Cobra, only 12 remained mechanically operational after 1 week of combat movement. The remainder sat disabled by fuel pump failures, final drive breakdowns, transmission seizures, and electrical fires that had nothing to do with enemy action. Meanwhile, captured Sherman tanks continued operating through conditions that would have destroyed entire German armored battalions. The standardization that American industry achieved became a source of both admiration and despair among German technical personnel. Sergeant Hans Miller of the 116th Panzer Division discovered that Sherman tank parts manufactured in different American cities were completely interchangeable without modification. He could remove a road wheel assembly from a tank built in Detroit and install it perfectly on a vehicle manufactured in Philadelphia using only standard field tools. German Panthers required individual adjustment of components, even when produced in the same factory, making field repairs dependent on specialized equipment that rarely reached frontline units. September 1944 brought the ultimate demonstration of Sherman reliability during the Allied pursuit across France. German reconnaissance units reported American armored columns maintaining advance rates of 60 miles daily, while German panzer units struggled to cover 20 miles without mechanical breakdowns. The 9th Panzer Division's intelligence section noted that American tank units seemed immune to the logistical difficulties that paralyzed German armored operations. Sherman tanks crossed France using fuel consumption rates that German engineers had calculated as impossible for vehicles of comparable weight and performance. The fuel efficiency advantage became critical as Germany's synthetic fuel production collapsed under Allied bombing. Captured Shermans delivered twice the miles per gallon of German designs, while operating on lower quality fuel that German engines couldn't process without damage. The Ford GAA power plant burned 87-octane gasoline efficiently, while Maybach engines required 100-octane aviation fuel that was increasingly unavailable even for Luftwaffe aircraft. American automotive engineers had designed military engines that functioned on whatever fuel was available, rather than demanding optimal petroleum products. By October 1944, German tank recovery units were routinely converting captured Sherman chassis into specialized vehicles, rather than attempting to repair their own disabled armor. The reliability of American automotive components made Shermans ideal platforms for mobile workshops, ammunition carriers, and command vehicles that needed to operate continuously without mechanical support. Obergefreiter Friedrich Weber of the 2nd Panzer Division explained to his commanding officer, "Sir, we can keep the American tanks running with mechanics who learned their trade on farm equipment. Our own panzers require factory engineers who died in the bombing raids." The electrical systems in Sherman tanks revealed American understanding of automotive reliability that German military contractors had never achieved. Wiring harnesses routed through protected channels resisted combat damage, while German electrical systems failed when subjected to normal battlefield vibration. The Sherman's electrical architecture used automotive-grade components that had been proven in millions of civilian vehicles, while German tanks employed military-specific systems that hadn't been thoroughly tested before mass production began. Component accessibility represented another dimension of American engineering superiority that German designs had sacrificed for theoretical performance advantages. Sherman mechanics could replace major drivetrain components without removing engines from chassis, reducing repair time from weeks to hours. German tank designs required complete disassembly for access to critical systems, making field repairs impossible under combat conditions. The American approach reflected practical understanding that combat vehicles needed to be maintained by soldiers rather than factory specialists. The psychological warfare impact of Sherman reliability extended beyond individual tank crews to entire German armored formations. Panzer commanders who had once relied on superior German engineering now faced an enemy whose mechanical advantages seemed insurmountable. General Heinz Guderian himself acknowledged in his personal correspondence that American industrial methods had created military vehicles that German industry couldn't match, despite having superior metallurgy and precision manufacturing capabilities. Winter 1944 brought the ultimate test of automotive reliability during the Battle of the Bulge. German armored spearheads that had been carefully husbanded for the offensive suffered catastrophic mechanical failure rates in the opening days of the attack. Kampfgruppe Piper lost more vehicles to breakdowns than enemy action, while American armored units maintained operational readiness despite hasty defensive movements across frozen terrain. The contrast became stark when German units discovered abandoned American supply depots containing spare parts inventories larger than entire German armored divisions possessed. The maintenance philosophy that supported Sherman operations revealed American understanding of mechanical reality that German perfectionist approaches had ignored. American field manuals assumed that all mechanical systems would require routine service, while providing procedures that minimized downtime and skill requirements. German maintenance doctrine reflected engineering arrogance that assumed superior design would eliminate the need for extensive field support, leaving crews unprepared when components reached their actual operational limits. Quality control in American tank production achieved consistency levels that German industry never matched despite having more experienced workers and better metallurgical knowledge. Sherman tanks manufactured in different facilities by different contractors met identical specifications without requiring individual adjustment or modification. German production involved multiple manufacturers whose interpretation of engineering drawings created compatibility problems that made maintenance logistics nearly impossible to manage effectively. The suspension systems that carried Sherman tanks across European battlefields demonstrated American engineering priorities that German designers had rejected in favor of theoretical superiority. Simple vertical volute springs could be manufactured quickly, installed easily, and repaired by mechanics with basic training. German torsion bar systems required precision adjustment and specialized tools that made field maintenance dependent on factory support that rarely reached combat units. By early 1945, the pattern had become undeniable to German technical personnel, who examined captured American equipment. Sherman tanks represented industrial philosophy that prioritized collective reliability over individual performance, practical maintenance over engineering elegance, and proven technology over cutting-edge innovation. These priorities had created an automotive foundation for armored warfare that German industry couldn't replicate despite having theoretical advantages in metallurgy, precision manufacturing, and engineering expertise. The final irony emerged during Germany's collapse when Wehrmacht units actively sought to capture Sherman tanks rather than defend their own armor. German tank crews preferred operating American vehicles that would function reliably rather than German designs that promised superior performance but delivered a mechanical frustration. The psychological transformation was complete when soldiers who had been taught about German engineering superiority voluntarily abandoned their own tanks to fight and captured American equipment. The Spring Offensive of 1945 revealed the ultimate vindication of American automotive philosophy as German resistance crumbled across multiple fronts. Obergefreiter Hans Dietrich of the 12th SS Panzer Division stood beside his disabled Panther tank on the outskirts of Nuremberg, watching American Sherman columns advance with mechanical precision that his own unit could no longer match. The Panther's final drive had failed after only 90 kilometers of combat movement, stranding 45 tons of sophisticated armor that represented the pinnacle of German engineering achievement. Across the battlefield, Sherman tanks continued their relentless advance with automotive reliability that seemed to mock every assumption German industry had made about mechanical warfare. The maintenance records that Dietrich discovered in abandoned German supply depots told a devastating story about the collapse of Wehrmacht armored capability. His own battalion had begun the year with 38 operational Panthers, vehicles that embodied Germany's most advanced metallurgy and precision engineering. By March 1945, only 6 remained mechanically functional, with the remainder scattered across Central Europe as monuments to automotive complexity that had exceeded practical sustainability. The mathematics of mechanical failure had rendered German armored doctrine obsolete, transforming the most technically sophisticated tanks in the world into elaborate roadside obstacles. The contrast became even more stark when German recovery units attempted to salvage their own disabled armor while observing American maintenance procedures through field glasses. Sherman tanks that suffered combat damage returned to service within hours using field expedient repairs that German technical manuals claimed were impossible. American mechanics replaced entire engine assemblies in combat zones using portable hoists and standardized tools, while German repair procedures required factory-level facilities that no longer existed. The automotive engineering that had seemed crude to German designers proved devastatingly effective when subjected to the ultimate test of sustained combat operations. Feldwebel Otto Kessler of the 1st SS Panzer Division documented the psychological impact on his mechanics as they watched American armored units maintain operational tempo that Wehrmacht formations couldn't achieve even under ideal conditions. His daily reports, discovered decades later in captured German archives, revealed the demoralization spreading through technical personnel who had been trained to believe in German engineering superiority. American tanks operated continuously for weeks without major maintenance, while German crews measured their vehicles' combat lifespan in days before critical systems failed catastrophically. The fuel efficiency advantage that Sherman tanks maintained became critical as Germany's petroleum situation collapsed entirely during the final months of the war. American armored columns advanced across Germany, consuming fuel at rates that German logisticians calculated as impossible for vehicles of comparable performance. The Ford GAA engines delivered consistent mileage while operating on captured German fuel stocks that Maybach power plants couldn't process without severe performance degradation. American automotive engineers had created military engines that adapted to available resources rather than demanding optimal operating conditions. The electrical systems in captured Sherman tanks continued functioning under conditions that destroyed German equivalents within hours of exposure to combat environments. Wiring harnesses protected by automotive-grade insulation maintained circuit integrity while German electrical systems failed from moisture infiltration and vibration damage. The American approach treated electrical reliability as essential to mechanical performance, while German designs assumed that sophisticated engineering would overcome environmental challenges through theoretical superiority rather than practical durability. Component standardization across American tank production became a source of profound frustration for German technical personnel who understood its implications for sustained armored operations. Parts manufactured in Detroit fit perfectly with components produced in Philadelphia or Chicago, allowing American field units to maintain their equipment using supplies from any source. German tank production involved multiple manufacturers whose interpretations of engineering specifications created compatibility problems that made logistics support nearly impossible under combat conditions. The suspension systems that carried Sherman tanks across European battlefields absorbed punishment that would have destroyed German torsion bar assemblies within kilometers of rough terrain operation. Vertical vollet spring bogies could be repaired using common tools and basic mechanical skills, while German suspension components required specialized equipment that existed only in factory environments. American engineers had designed automotive systems that anticipated battlefield damage rather than assuming that superior engineering would prevent mechanical stress. Quality control procedures in American manufacturing achieved consistency levels that German industry never approached, despite having more experienced craftsmen and superior metallurgical knowledge. Sherman tanks built by different contractors in various locations met identical specifications without requiring individual adjustment or modification. German production standards varied between facilities, creating maintenance nightmares for field units that received vehicles requiring different procedures and incompatible spare parts inventories. The automotive accessibility that American designers incorporated into Sherman tanks allowed mechanics to perform major repairs without specialized training or exotic tools. Engine compartments provided clear access to critical components, while German designs required complex disassembly procedures that made field maintenance dependent on factory-trained specialists. The American philosophy treated tanks as mechanical devices that soldiers would need to repair rather than precision instruments requiring expert attention. By April 1945, German armored units were actively abandoning their own vehicles to operate captured American equipment whenever possible. Tank crews who had been indoctrinated about German engineering supremacy voluntarily transferred to Sherman tanks that would function reliably rather than struggle with indigenous designs that promised theoretical advantages but delivered mechanical frustration. The psychological transformation was complete when Wehrmacht soldiers chose enemy equipment over their own nation's most advanced military technology. The final drive failures that plagued German heavy tanks became symbolic of broader industrial philosophy problems that American automotive engineering had avoided through systematic design approaches. Panther and Tiger final drives lasted an average of 150 kilometers before requiring complete replacement, while Sherman final drives operated for thousands of kilometers without major intervention. German engineers had pursued theoretical performance maxima, while American designers focused on practical operational requirements that reflected actual battlefield conditions. The maintenance schedules that supported Sherman operations revealed American understanding of mechanical reality that German perfectionist approaches had systematically ignored throughout the war. American field manuals provided maintenance procedures that assumed normal component wear while designing service intervals that minimized operational downtime. German maintenance doctrine reflected engineering arrogance that treated routine service requirements as admissions of design failure rather than necessary aspects of mechanical operation. Engine cooling systems in Sherman tanks maintained operational temperatures under conditions that caused German power plants to overheat and seize catastrophically. American automotive engineers had incorporated cooling capacity margins that anticipated combat loading, while German designs assumed optimal operating conditions that rarely existed in battlefield environments. The practical understanding of thermal management that American industry possessed exceeded German theoretical knowledge because it had been validated through millions of civilian vehicle applications. The transmission systems that transferred power from Sherman engines to driving wheels functioned reliably under combat loads that destroyed German equivalents within hundreds of kilometers of operation. American automotive transmissions used proven technology that had been refined through decades of civilian application, while German military transmissions employed cutting-edge designs that hadn't been thoroughly tested before mass production began. The contrast became devastating when battlefield conditions revealed the difference between theoretical capability and practical reliability. The spring-loaded road wheels that supported Sherman tanks across European terrain maintained ground contact while absorbing impacts that would have damaged German rigid mounting systems permanently. American suspension engineers understood that battlefield mobility required components capable of repeated shock absorption rather than precision systems optimized for theoretical performance. The vertical volute spring bogies represented automotive engineering philosophy that prioritized practical durability over technical elegance. Fuel pump reliability became another dimension of American automotive superiority that German industry had failed to achieve despite having superior precision manufacturing capabilities. Sherman fuel systems operated continuously without the spontaneous failures that plagued German designs throughout their service lives. Panther fuel pumps caused engine fires that destroyed entire vehicles, while Sherman fuel delivery systems maintained consistent performance under conditions that would have challenging systems that operated Sherman turd any mechanical system. The hydraul-ret traverse and gun elevation mechanisms functioned reliably using automotive-grade components that German military contractors had rejected as insufficiently sophisticated. American engineers applied hydraulic technology proven in industrial applications to create military systems that operated consistently under combat conditions. German hydraulic systems employed theoretical advanced designs that failed catastrophically when subjected to battlefield stress and maintenance neglect. Electrical generation and battery systems in Sherman tanks maintained power supply consistency that kept fighting systems operational during extended combat engagements. German electrical systems suffered voltage regulation problems that caused equipment failures when vehicles operated at varying engine speeds. American automotive electrical engineers had solved power management problems through civilian vehicle development, while German military systems assumed optimal operating conditions that rarely existed in combat environments. The gear reduction systems that connected Sherman engines to final drive assemblies delivered power efficiently while operating within design stress limits that German engineers had exceeded in pursuit of theoretical performance advantages. American automotive engineers understood that drivetrain longevity required conservative design margins, while German military contractors pushed components beyond practical operational limits to achieve specification superiority that existed only on paper. Component heat treatment and metallurgy in American tank production achieved durability standards that German industry couldn't replicate, despite having superior theoretical knowledge of materials science. Sherman drivetrain components operated for thousands of miles without failure, while German equivalents suffered metallurgical problems that caused catastrophic breakdowns within hundreds of kilometers. American manufacturing quality control ensured consistent materials properties, while German production standards varied between facilities and individual components. The oil filtration and lubrication systems that protected Sherman mechanical components maintained engine and transmission life under conditions that destroyed German equivalents through contamination and inadequate circulation. American automotive engineers had developed filtration technology through civilian applications that German military contractors hadn't incorporated into their designs. The practical understanding of lubrication requirements that American industry possessed exceeded German theoretical knowledge because it reflected actual operating experience rather than laboratory conditions. As the Third Reich collapsed in May 1945, the final assessment of German tank reliability came from Wehrmacht personnel who had operated both indigenous and captured equipment under identical conditions. Their unanimous conclusion was that American automotive engineering had achieved practical superiority that German theoretical advantages couldn't overcome. The Sherman tank represented industrial philosophy that prioritized collective reliability over individual performance, creating mechanical foundations for armored warfare that German perfectionist approaches had failed to match despite having every apparent advantage in engineering expertise and manufacturing capability. The evidence mounted relentlessly through captured German technical reports that documented the superiority of American automotive engineering in ways that shattered Wehrmacht confidence completely. Hauptmann Friedrich Steiner of Army Group Center's Technical Evaluation Unit submitted a classified assessment in April 1945 that would never reach higher command due to Germany's communications collapse. His findings, discovered in abandoned field headquarters near Leipzig, revealed the devastating scope of American mechanical advantages that German industry had consistently underestimated throughout the conflict. Steiner's report documented fuel consumption tests conducted on captured Sherman variants under identical conditions to German tank operations. The results defied every assumption German engineers had made about automotive efficiency relationships between weight, power, and fuel economy. Sherman tanks achieved 1.8 miles per gallon, while carrying full combat loads across terrain that reduced German vehicles to 0.7 miles per gallon under similar circumstances. The Ford GAA power plant delivered consistent performance using 87-octane gasoline, while Maybach engines required 100-octane aviation fuel that no longer existed in German supply systems. The transmission durability tests that Steiner conducted revealed American automotive engineering sophistication that German military contractors had never achieved despite having access to superior metallurgical knowledge and precision manufacturing equipment. Sherman transmissions operated for 2,500 miles of combat conditions before requiring a major overhaul, while German equivalents averaged 400 miles before catastrophic failure. The American approach incorporated design margins that anticipated battlefield stress rather than pursuing theoretical maximum performance that existed only under laboratory conditions. Electrical system reliability became another dimension of American superiority that German technical personnel documented with growing desperation as their own equipment failed systematically. Sherman electrical harnesses maintained circuit integrity for thousands of miles, while German systems suffered insulation breakdown and connector corrosion within hundreds of miles of operation. American automotive engineers had solved electrical reliability problems through civilian vehicle development, while German military contractors employed theoretical advanced designs that hadn't been validated through extensive field testing. The cooling system efficiency that kept Sherman engines operational under combat loading conditions revealed American understanding of thermal management that German designers had overlooked in their pursuit of power density optimization. American radiators and cooling fans maintained operational temperatures during sustained high-power operation, while German systems overheated and seized when subjected to combat demands. The practical thermal engineering that American industry possessed exceeded German theoretical calculations because it reflected actual operating experience rather than mathematical projections. Suspension component longevity provided additional evidence of American automotive engineering superiority that German technical evaluators found increasingly difficult to explain within their industrial worldview. Sherman vertical volute springs operated for thousands of miles while absorbing battlefield impacts that destroyed German torsion bar assemblies within hundreds of miles. American suspension engineers had designed components capable of repeated shock absorption rather than precision systems optimized for theoretical performance under ideal conditions. The hydraulic systems that operated Sherman turret, traverse, and gun elevation mechanisms functioned reliably using automotive-grade components that German military specifications had rejected as insufficiently sophisticated for armored vehicle applications. American engineers applied hydraulic technology proven in civilian and industrial applications, while German contractors employed cutting-edge designs that failed catastrophically when subjected to battlefield maintenance neglect and environmental contamination. Quality control consistency across American tank production achieved uniformity standards that German industry never approached, despite having more experienced craftsmen and theoretically superior manufacturing processes. Components manufactured in different American facilities by different contractors met identical specifications without requiring individual adjustment or fitting procedures. German production involved multiple manufacturers whose interpretation of engineering drawings created compatibility problems that made field maintenance dependent on specific factory support. The parts interchangeability that American standardization achieved became a source of profound tactical advantage that German logisticians recognized too late to influence strategic planning. Sherman components manufactured in Detroit fit perfectly with assemblies produced in Philadelphia or Chicago, using only standard field tools and basic mechanical procedures. German tank production created vehicles that required individual adjustment, even when manufactured in identical facilities using supposedly identical processes. Maintenance accessibility in Sherman designs allowed field mechanics to perform major repairs without removing engines from chassis or requiring specialized lifting equipment that rarely reached frontline units. American engineers had incorporated service access that assumed tanks would be maintained by soldiers using common tools rather than factory specialists with exotic equipment. German designs required complex disassembly procedures that made battlefield repairs impossible under combat conditions. The Sherman's triumph over German engineering excellence represented more than mechanical superiority. It embodied industrial philosophy that valued reliability over complexity, proven solutions over theoretical perfection. When German tankers abandoned their sophisticated Panthers for captured American armor, they admitted defeat not just in battle, but in the fundamental approach to mechanical warfare. The reliable rumble of Sherman engines crossing European battlefields announced that practical engineering had conquered perfectionist dreams, forever changing how nations would design their fighting machines.